reach the ground.
Alright, so I have here an extremely rare 8-pound weight. Okay, so I'm going to explain to you the difference between mass and weight, because even though it's very easy, a lot of people mess it up still today in the 21st century. Okay, so this weight has a set mass, and mass is how much matter in this object. So how big it is and what all is in it never changes. Mass never changes no matter where you are, unless I were to cut this in half. Then the mass would be different because it'd be two different things and all that. But the mass doesn't change. The weight, however, is the force of gravity, and that's found by multiplying the mass times the acceleration. And the acceleration due to gravity on Earth is 9.8 meters per second squared. But if I were to go to another planet like Jupiter and take this lovely weight with me, the acceleration or gravity will be a lot higher because Jupiter is a bigger planet, so the weight would be different. Because there's a force of gravity on it would be higher because of acceleration, but the mass always stays the same. No matter what, this will always have the same mass, but the weight will change depending on where it is.
Okay, let's talk about net force. Net force is the total amount of force that is applied by an object. Right here you can see that the bottle is not moving, so we obviously know it's in equilibrium, or the net force on it is 0. This is because the bottle has a mass of its own, and the acceleration due to gravity is pulling it downwards. However, it also has a normal force, which is pushing back up, and they both equal out, which makes the net force of this bottle 0, which is why it's not moving. However, once I apply a force in my hand, this changes the net force, and it no longer becomes equilibrium. This is due to the fact that because the force of my hand is stronger than the force of friction between the bottle and the counter.
So basically what Duke is saying is that whenever the water bottle is just sitting there, the net force is 0, because the only two forces acting on it are the force of gravity, which are pushing down on it, and the normal force from the table, which is keeping it up. These forces combined equal 0. And it's not moving because there's no other force acted upon it until Duke takes his hand and pushes it, like I'm pushing this. And whenever he pushes it, or when I push this, the net force is greater than 0 because I am applying a force and moving it, and it is no longer standing still.
Look what we got here, a wild pear. The mass of the pear times the acceleration due to gravity is equal to the force of the tension in the rope. The tension force is equal to the weight of the pear in newtons, and the net force is 0 because the tension force balances out the weight of the pear.
Tension force
The
is
force
the...
that is transmitted through the string, rope, or cable or wire that is pulled tight by the forces acting from opposite ends. The tension force is directed along the length of the wire and pulls equally on the objects on the opposite ends of the wire.
So friction is the resistance that one surface or object encounters when moving over another. For example, the friction in a tire moves, the force of friction moves opposite of the direction of motion. So as the tire spins and propels the car forward, friction works backwards as the tire spins and makes contact with the ground and pushes the car backwards while the forward motion goes forward. So basically all you need to know is that friction occurs when two objects rub or slide past one another. Now there is two things though. With friction there's something called static friction and then kinetic friction. Static friction occurs when an object is at rest. And when you try to move that object, static friction prevents that object from being moved. But once you break with that initial push, you break the static friction of the object at rest. It'll be hard to push, but then all of a sudden it'll be easy because you broke the static friction between the object and the surface. And then you'll move on to kinetic energy or kinetic friction, which is a lot easier to overcome. Alright, so now we're going to talk about centripetal force. Now, centripetal force occurs with circular motion and is a force that keeps an object spinning or revolving around a point, the center of the circle, so it keeps it connected to the center of the circle. So for instance, when you take a yo-yo and you swing it around, the string, which connects the center of the circle to the end, which is the yo-yo, and it spins, that string is what keeps it connected to the center. Therefore, the string is the centripetal force of that object in motion. So if you just watched that video, you saw the girl swinging around on the little play set. And what's happening there is her holding onto the bar acts as the centripetal force, because the centripetal force is always center seeking. And when she's holding onto the bar, her force is focused on staying at the center of the circle. But as she spins around and she lets go, that centripetal force is gone. There's nothing that's keeping her in contact with the center of the circle, and so she flies off in a straight line tangent to the circle, which is a whole other deal that we're not going to get into.
Newton's first law states that an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. So the bouncy ball here at rest will stay at rest infinitely until acted upon by an unbalanced force, while the bouncy ball in motion will stay in motion until the same thing happens. But on Earth we have air resistance and friction which play parts in the movement of the bouncy ball, so unless we're in space or some other ideal setting, air resistance and friction can affect the movement of the bouncy ball when it is in motion.
And for this example, I'm going to be sitting in the back of the Subaru, and the car is going to accelerate, and it's going to throw me backwards and then throw me forwards.
Mother of God!
And this occurs because my body, which is in a constant motion downwards towards the center of the earth due to gravity, it wants to stay in that motion, but as the car accelerates from underneath me, I'm wanting to stay in that singular motion, but it'll throw me backwards because the ground underneath me is changing. Now, as I accelerate with the car, I'll eventually reach equilibrium again, moving forward with the car, but as the car deaccelerates, it'll throw me forward because I want to keep going the way that I was going before. My inertia will kick in and I will keep going forward while the car stops, which is why I'm thrown forward.
Alright, so here's another example of Newton's first law. You got this really creepy zombie down here, okay? It's got the brown hair and the green skin, it's got blood on its mouth, okay? It's really creepy. It is at rest, okay? It's not moving. It's just standing completely still on top of this desk. So, it is going to stay at rest unless acted upon by an unbalanced force. So, years could go by and there could be no unbalanced force and it'll still be at rest. Until this comes along, an unbalanced force. And as you can see, creepy zombie was not at rest until now because he's not being acted upon by an unbalanced force. Thanks for watching.